Hi students, so today I'm talking about the nuclear magnetic resonance, Nmr spectroscopy under analytical techniques, reference from the organic chemistry with biological applications, John E. McMurray, chapter 10 and 11. Okay, so Nmr, understand the terms first. Nuclear, in this case, means in the nucleus, right at the core, where your protons and neutrons are. Magnetic means involve magnets. Not magneto, just magnets. And as we know, spectroscopy is all about electromagnetic wave. So in NMR, we'll be using radio wave kind of frequency that can cause a change in the nuclear spin states using a magnetic field. This portion here, which is really harmless because they're very low frequency, low energy, but long wavelength. Now, in the hydrogen nucleus, this is the most studied element for NMR spectroscopy. We know that the nucleus of the hydrogen atom has a very weak nuclear spin, and so that it behaves like a very weak compass needle, always swivel around, doesn't stop at somewhere, weak. Now, if a molecule that contains hydrogen is placed in a strong magnetic field, the external magnetic field that's outside there, I put the force on it, imagine magneto is around you, then the magnetic hydrogen nucleus would line up with the spin, because that guy is very strong. It says, okay, turn this way. You line up. Or if I change the external magnetic field, say change spin, change, so you go down. Okay, but although it normally lines up in the applied magnetic field, that means according to the instruction of this guy who says it, it can also change on its own because it doesn't behave. You see, it doesn't mean when the command is given, the soldier will follow. Of course, he should follow, but there's a tendency that the soldier may not follow. So why the soldier follows is, or why the electrons follows the command of this magnetic field, because it's energetically more favorable. But on the other hand, there could be some circumstances where it doesn't follow. So which is a bit higher energy, it doesn't follow the external magnetic field. Now, not all the nucleus requires the same amount of energy to change this spin. You see, flipping the spin, it is aligned with this external magnetic field to the one that's against it. Against means high energy, disobeying the order. To obey the order, you get a very easy life, you don't get scolding, so lower energy. Now, the exact amount of energy, this absorption, the gap between the E1 and the E2, depends on the chemical identity, the element, who they are, hydrogen, carbon, phosphorus, etc. And the environment of the nucleus, this element with the surrounding. So if we talk about the hydrogen in a methane molecule, CH4, it's going to be a different hydrogen in environment in acetone, propanone with a CO double bond. And the amount of energy here also depends on how many nucleus are there in the environment, which means if I have a alkane, for instance, simplest alkane, your methane CH4 against your propane C3H8, then the amount of energy differs as well. Now we know that when we spam some radio wave, right, only with the fixed amount of energy that fits to that proton, it will cause a flip in the spin for that particular proton. Okay, and once it relaxes, we get the emission of the same amount of energy. So this energy that we measured can give us information about the environment of the hydrogen that it is in. And it also tells us how many hydrogen atoms are in that particular environment. So let's say I have methane, CH4. If you talk about it, all the 4 hydrogens are attached to the same carbon. So they are actually in the same environment. So in the spectra of NMR for methane, there's only one signal because they are all identical. Now, in the spectra for NMR, we can also determine the peak positions, and this tells us about the energy released and the different environment of the protons. The peak positions of the NMR is given by what we call the chemical shift. Alright, we are using the delta sign in the Greek alphabet. Okay, so Greek letter delta, and the scale for NMR normally ranges from 0 to 15 parts per million. Again, do not memorize this table. It should be given to you. Okay, these values are not important. What you're going to do is to refer to them and say, okay, it should belong to this functional group that I have a prediction to make, and it makes the right logic to the conclusion of, based on what I have, you see, all the information that I got, I can come up with this structure. So this is an example of Nmr Spectra that you might see in the lab. Like I said before, proper known, because you see a symmetry line here, so these 3 protons are exactly the same as these 3 protons. So that means these 6 are all equivalent. Now, I said earlier that if these protons are joined to the same carbon, they are the same. So similar environment, and hence in this spectra you only see one peak, one signal. Okay. So in practice, you have this equation here that this is the frequency, then we keep constant, and then we change the external magnetic field here. And your mu here is a gyromagnetic ratio. There's something inherent towards the proton itself. So in a spectrum, you have to differentiate between up field and down field, and high field and low field. So down field means high chemical shift, which means low field. Up field means towards 0 ppm, high field, and low chemical shift. Now, many different kinds of nucleus, they exhibit NMR phenomenon. Not all of them, but most of them. So who are the magnetic nuclei? Proton 1, hydrogen 1, carbon 13, take note, not carbon 12, the most common abundant one. Hydrogen 2, deuterium, nitrogen 14, fluorine 19, phosphorus 31. So the non-magnetic nuclei will include carbon 12, oxygen 16, sulfur 32. So if we want to investigate these elements, you can't use NMR spectroscopy. Each chemically distinct nucleus in the molecule has a slightly different electronic environment and consequently a different effective field. Each chemically distinct carbon-13 or hydrogen-1 nucleus in the molecule experience a different kind of effective field, and they experience a different and very distinct kind of an NMR signal that pertains to them only. It's very special. So like I mentioned in the previous slide, we have the external strong magnetic field, and if the nuclear spin is aligned with it, it is of a low energy because that's easy, following the order, but it can absorb some energy to be more energized and goes against it. It goes down, opposite spin compared to the external magnetic field. Now there's something called the shielding, the spin against the magnetic field. So we know the nucleus, we have electrons, right, that shields it, and electrons can have spin. So if you compare the nuclear spin of a fluorine and of a carbon, it's different because fluorine is more electronegative. So it will draw electrons away from the proton that's nearer to it, and hence the proton's nuclear spin is more susceptible to the external magnetic field, and hence you have a higher chemical shift. I'll elaborate a bit later on. So for the proton chemical shift, the hydrogen in the functional group that have electron withdrawing groups, atoms like fluorine, iodine, bromine, CO double bond here, they are being deshielded with a high chemical shift, so they appear in the down field, low field. Okay, you can see very easily your aldehyde, your carboxylic acid, right, CO, C double bond O, they draw electrons. You see this proton here, the signal become having a very high chemical shift. Whereas if you compare something very ordinary, such as your alkane, alkene, right, they are of a higher field, not the low field. So this 0 ppm, this is our reference point, is our standard called tetramethylsilane. Tetra means 4 times methyl group silane. You know, silane, silicon with hydrogen, methane, silane. You get the analogy?